In 210, let's think about tangent line approximation. So when we're doing an approximation using tangent lines, what we want to do is we want to have some value a that's really close to the one that we really care about. Typically we pick this so it's a nice number, so when we do our computations it's going to work out pretty nicely. But we want it as close as possible as we can to the one we really care about, whatever that value happens to be. Now, we're given a formula here, but let's talk a little bit about where this formula kind of comes from first. All right, so to do so, I'm going to think about the point-slope form of a line. Y minus y1 equals m times x minus x1. A formula you should have seen at this point along the way. But let's think about it, first of all, in function notation. So x1, y1, that goes as the ordered pair that we know that's on our line. All right, in function notation, that's going to go along with a is the value that we're choosing, right? That's an x value. And we're going to plug it into the function, so that's going to give us f of a is the output value. Because we think of our y's as corresponding with f of x. Now the other thing that we can kind of fit together, since we know about derivatives at this point, we can think about the slope of a line is going to correspond to that derivative, but in this case we're going to evaluate it at our x value of a. So let's plug things in where we know they should go. All right, we said y was going to go along with f of x minus, well, we said y1 corresponds with f of a, the y value of that ordered pair. We mentioned that the slope matches up with f prime of a. And then all that remains here is we don't know x. And then we did say that a was going to be the x value for that point. All right, let's rearrange this and isolate the f of x on one side by itself. Now I'm going to use my approximation symbols in between here. And all I have to do is I have to move that f of a to the other side. So I'm going to add that f of a to move it to the other side, and we get the same formula as what was given to us in our book. The only difference is I've placed my f of a at the end as opposed to in front, but either one means the same thing. Let's use this formula now to try to get an approximation. So suppose we know that g of 20 is going to equal 5, g prime of 20 equals 1.4, and we want to use this information to try to approximate g of 23 and g of 18. So I've used the same formula, just written with f primes and f instead of g and g primes. So to approximate this, let's approximate g of 23 first. So g of 23 is going to be g prime of 20. We're choosing 20 is going to be our value for a. So g prime of 20 multiplied by 23 was our x value over on the left side, minus 20 was our a value, plus g of 20. Filling all this information in, g prime of 20 goes as 1.4. Then 23 minus 20 makes 3 on the inside here, plus g of 20 goes as 5. A little bit of simplifying down here, and we can say g of 23 is going to be 1.4 multiplied by 3 plus 5. Works out to be approximately, I probably should use my approximately signs, squiggly equal signs in between here, about 9.2. Now let's do the same thing, but this time we're going to use 18 is going to get filled in here. So we can approximate g of 18. It's going to be approximately, again, we go g prime of 20, 18 minus 20, plus g of 20. So the only component that changed in this one from the first one was when we used 18 here, as opposed to the first time through we used 23 right in this spot. Everything else remains the exact same. So this is going to be approximately, again we can fill in 1.4 for our derivative. This will be negative 2 on the inside of our set of parentheses, plus 5 at the end. This works out to be approximately 2.2. Now, how good of an approximation these are, we're not really sure on this function. We've just been given a little bit of information on g of x. But the closer these values are together, the better approximation it is. You'll notice they did choose a couple values. 23 was fairly close to 20. Also 18 was fairly close to our 20 as well. But the closer the better as far as getting a better and better approximation. So I hope this helps out as you're working on tangent line approximation. Good luck.